And just remember that what I'm about to show you, for some of you, it's going to just be clear as a day. You're going to get it. You're going to be able to do it. You won't need repetition or thinking about it. Others of you, there may be a little sort of a spectrum where some of you are going to be like, I need help. This doesn't make any sense. Others of you, it's gonna make sense, but you're also gonna need some processing time. And I am more than happy to talk things through with you. We'll have time today to talk about stuff, and we'll also have time outside of class down the road. Look, it's gonna do it again. How do I make this default to what I obviously want it to look like? Does anybody know? Anybody here Excel expert? Okay, well, your job is to figure it out. If you can figure it out, I will give you an A for both semesters in the entire year if you help me solve this one little technological problem. Does that seem like a reasonable deal? Yes. You won't have to do anything. You don't have to turn anything in. You don't even have to come to class. You're just to help me solve a problem, and I'll give you an A. That's not true. All right, so the first technique that I'm going to show you, so remember Tuesday, we were talking about how you can interpret the graphs, and we had a position versus time graph, and we saw, like, if the slope of the line is steeper, you're going faster. If the slope is up, you're going in the positive direction, which with our sensors is typically away from the sensor. And if it's in the negative direction, if it's a negative slope, you're moving in the negative direction, which is in our sensor universe toward the sensor. Basically, what's really interesting about this is, even though it's a position versus time graph, you can figure out a whole bunch about speed. Faster, slower, toward the sensor, away from the sensor, holding still. That's not position. It's position and time together. It turns out that from a position versus time graph, you can actually construct the corresponding velocity versus time graph. We can figure out how fast something is going, for how long it's going that fast, from a position versus time graph. So I'm going to show you how to do that, and then today you'll have some time to play around with it with the motion match exploration. There will also be, we'll have practice problems that we do, and there's going to be another a formal lab that I assign you next week. The first thing you're going to do with the position versus time graph is you identify sections of the graph that have different slopes. So if this is my position versus time graph, then I can see there's a section here between 0 and 2 seconds with this slope. There's a section between 2 and 4 seconds with this slope. There's a section between 4 and 4.5 seconds with this slope. There's a section between 5.5 and 6 seconds, a section between 6 and 8, between 8 and 9, and between 9 and 11. So I've identified the sections of the graph with different slopes. And then the way to actually find the speed during those sections is to calculate the slope. And if you don't remember this, slope, the variable is m, is typically the variable we use for slope. It's just the change in your y coordinate divided by the change in your x coordinate. In this case, our y coordinate is position, and our x coordinate is time. So what this is going to tell us is change in position divided by change in time. If the section that you're looking at is a straight line, then the slope throughout that section is the same. If the section that you're looking at is a curved line, then it's speeding up or slowing down. The slope isn't the same the whole time, and it gets a little trickier. And I'm not going to tell you how to do that now. I will tell you how to do that down the road. We'll play around with it a bunch, but I'm going to let you experiment with it and see what you can figure out on your own when the time comes. For now, we're just going to deal with these stretches. Remember, we said straight lines represent constant speeds and directions, constant velocity. Okay? So we can calculate the slope, and I'm going to do this math in my head because I can, but two things. Number one, if you can't do the math in your head, you're welcome to use calculators whenever you need to. The other thing is check my work, because when I do mental math, I make mistakes. And if I make a mistake, it's not on purpose. So those of you who are good with mental math, double check me on all of this stuff, all right? I think most of these are gonna be like pretty straightforward. This has a slope of 0. So does this, so does this. So that's pretty easy. This moves down 10, so the rise is actually negative, right? It's not going up, it's going down, so this is negative 10, and it's a change of 2 seconds. Negative 10 divided by 2 is going to be negative 5. This section is much steeper. It goes down 15, so that's negative 15, and it does it in a half a second. So negative 15 divided by 0.5 is negative 30. This section right here is positive. It's going up. It goes up 15, and it does it in 1 second. So this should have a slope of positive 15. And this goes up 15, but it does it in 2 seconds. So this has a slope of positive 7.5. Does that look right? Anybody see any mistakes? Okay. So step 1, identify sections with different slopes. Done. Calculate the slope with rise over run. Done. What do you do if the line is curved and it's not a constant slope? You don't know yet. You are going to have a chance to figure it out on your own. I will also tell you, so I'm not going to leave you, I'm not going to make you like struggle with it. I just want you to try it on your own and see where you can get. And then to make the velocity versus time graph, you just plot the slope for each section during the appropriate times. So I have one section between 0 and 2 seconds. I have one section between 2 and 4 seconds. I have one section between 4 and 5.5 seconds. One between 5.5 and 6. One between 6 and 8. One between 8 and 9. And one between 9 and 11. Okay, and I made, so this graph I just got from the internet somewhere. This graph I made myself, and I scaled it so that it matches up. It's not perfect if you look closely. When you do this, you should use graph paper. You don't have to do it for the motion match exploration, but down the road, I'm going to ask you to use graph paper, and the best way to do it is to make your position graph above the velocity graph, because then the times line up like vertically. So plot the slope. What does that mean? Well, here's my velocity, and this is 0, and I need to be able to plot numbers that go up to positive 15 and down to negative 30. So I've scaled this graph. You can see it's kind of weird, like it's sort of, it's not symmetrical. That's because I knew that I needed more negative values than positive values. If I make each one of these lines 5 meters per second, then I've got 5, 10, and 15 meters per second in the positive direction, and I've got 5, 10, 15, 20, 25, 30 meters per second in the negative direction. Okay? And when I say you plot the slope, what I mean is the y-axis value on our velocity versus time graph is going to be equal to the slope of the position versus time graph. Between 0 and 2 seconds, my slope was 0. That means the y value of my velocity versus time graph between 0 and 2 seconds is 0. Between 2 and 4 seconds, the slope is negative 5. So that means my y value between 2 and 4 seconds is going to be negative 5. Between 4 and 5.5 seconds, my slope is 0. So the y value of my velocity versus time graph is going to be 0. Between 5.5 and 6 seconds, the slope on my position versus time graph is negative 30. So the y value on my velocity versus time graph is going to be negative 30. Between 6 and 8 seconds, it's back to 0. Between 8 and 9 seconds, it's 15. And between 9 and 11 seconds, it's 7.5. So I've drawn horizontal lines here. Why are the lines horizontal? Because on a velocity versus time graph, constant speed is reflected by a horizontal line. On a position versus time graph, any straight line is constant speed. So I'm only going to have horizontal lines on my velocity versus time graph. There's something weird here, which is how are you moving from one speed to the next? And the answer is you must be speeding up or slowing down, right? Like if at first I'm not moving, and then I'm moving at -5 meters per second, I must have sped up in that direction. So once you've got your horizontal lines drawn, you can connect the lines on the graph. And this is where some of you might realize this is a little unrealistic because this is really, you're really speeding up quite quickly here. This is never what it would look like in real life. But on one of these graphs, Megan, Mathis, and Lillian, if you guys want to chat, go outside so other people can listen. You're welcome to do it, I just don't want you to do it in here. These vertical lines are really just kind of a placeholder, and what we're saying there is there was some change in speed that happened. We don't know what it really looked like. When you saw your own graphs using the motion sensors, and when you saw my graph using the motion sensor, what you realized, what you should have realized is this graph realistically would look more like this. It just doesn't, you don't really move at those speeds. If we had a computer and gears and wheels and like everything was like really precision driven, then you could come close to this. But you'd notice a couple of things. One is all of these lines, these vertical lines, if you zoomed in, would be slightly angled because it takes time to go from one speed to another speed. You can't do it instantly. So you're never going to have a perfectly vertical line. The other thing is that the corners, it's always going to be curved. Even if it, like, if you kind of zoom out and you look at it, it looks like this. If you were to zoom in, what you'll see is all of these lines are angled, all of these corners have curves. Okay? And that's something that's worth thinking about. If you, as you do this activity, if you're feeling pretty confident with the process, great, but you can think about what I just said. Why is it that I know? How do I know that these lines would never be perfectly vertical and the corners will never be sharp? Always going to have curves. You're always going to have diagonal lines. Okay. All right. So I said there's 3 things that you're going to need to do. One is make a velocity versus time graph from a position versus time graph. The next skill that I'm going to ask you to know how to do is how to find displacement from a velocity versus time graph. And we haven't talked about the definition of displacement yet. We will next week. But basically what displacement tells you is how far you've gone and in what direction. Okay. So what it boils down to is this. When you have a velocity versus time graph, you're showing on the y-axis a speed, and on the x-axis an amount of time. And if you think about, like, speed is distance over time, if you think about multiplying speed by time, you'll realize that should give you some indication of distance, right? So if speed is equal to distance over time, then if we multiply both sides of this equation by time, we should get something along the lines of distance equals speed times time. And it does sort of work. What you're going to see is that this equation is misleading. This isn't accurate. What this equation actually says is that average speed is distance over time. So that distance would be average speed times time. If you have a changing speed, then you have to find the average first. And we're gonna do that by using geometry. What we're gonna do, I'm gonna show you a technique, and then this, again, just remember, this may make perfect sense to you, or you may be like, what? Just remember, we're gonna iterate. So we'll do this again, we'll do this a few times, you'll have lots of practice, and most importantly, you'll have lots of time to think about it. So if you wanna find how far something moves, and in what direction, by using a velocity versus time graph, here's what you do. The first thing is, you draw actual geometric figures on your velocity versus time graph. Those geometric figures should be between the line, which is technically, even though these are all straight lines, we call it a curve because it's mathematical. You draw a shape between the curve and the x-axis. If you're interested in the entire period of time shown by the graph, then you do that everywhere. If you're only interested in part of the time period, how far did it move from 4 seconds to 6 seconds, then you only need to draw those shapes between 4 and 6 seconds. I'm going to do this for the whole thing so you can see the whole process. So I can see, these are like really easy geometric shapes here. The motion of the object is from 0 to 6 seconds. It speeds up to 10 meters per second, stays at 10 meters per second. It slows down, reverses direction, and ends up at 10 meters per second in the other direction, and then it moves at that speed for 1 second. What happens after this? We don't know. It might stop. It doesn't indicate that. It might speed up. We have no idea. It might keep going. All we know is between 0 and 6 seconds, these were the velocities. So the shapes that I'm going to draw here look like this. I can make a triangle between my curve and x-axis here. I can make a rectangle between my curve and the x-axis here. Another triangle here. Another triangle here. My curve is below the x-axis, so now my shape is below the x-axis. And then there's another shape here. It's a rectangle. So I have 1, 2, 3 triangles, 1, 2 rectangles, okay? So I've drawn squares or triangles between the curve, the velocity line, and the x-axis. And then I'm gonna find or estimate, in this case I can actually calculate it because I have the numbers, but with a real graph you might not be able to do that because you may be having to interpolate some of those numbers. And if there are curved lines, which there could be, then we don't really have math to deal with that. What we'll do instead is we're gonna just approximate. We'll draw some approximate triangles and approximate rectangles to kind of fill the space as much as we can. You don't have to worry about that for now though. We're just looking at straight lines. So we're gonna be able to actually calculate the area. And when I say you're gonna calculate the area of each shape, what I mean is sort of the geometric area. But you're not gonna calculate the geometric area by measuring the length of this line, the length of this line, multiplying them together and divided by 2. We're gonna use the axis to tell us the length and the width. The width of this shape, not geometrically, but from the graph, is 1.5 seconds. The height of this shape, again, not geometrically, but on the graph, is 10 meters per second. 1.5 times 10 is 15. This is a triangle, so we divide by 2 to get the area. So the area of this triangle is 7.5. And this was positive 10 meters per second, so the area of this triangle is positive 7.5. Let's look at that just in a little bit more detail, just for this first triangle, so that you can see how this works. What we're doing is we're saying that the area of our triangle is 1/2 base times height. The base of this triangle is 1.5 seconds. The height of this triangle is positive 10 meters per second. Remember dimensional analysis from chemistry? The seconds cancel here. Seconds cancel. So we get 1, 1/2 times 1.5 times 10, that is 7.5, and the units are meters. We get a distance when we multiply the x-axis value by the y-axis value for that shape. So what this is telling us is how far this object moved during that time period, 7.5 meters in the positive direction. If this were a sensor, what that would mean is wherever this object started, it moving at a constant, or moving at an increasing speed at a constant rate. It ended up moving 7.5 meters away from the sensor, if this was being measured by a sensor. All right, so this is positive 7.5. This is 1.5 seconds times 10 seconds. It's a rectangle. We don't divide by 2. So this is 15 meters. This is 1 second times 10 meters per second. It's a triangle, so we divide by 2. This is positive 5. This is 1 second times negative 10, and it's a triangle, so we divide by 2. So this is negative 5. And this is 1 second times negative 10 meters per second, so that's negative 10. From 0 to 1.5 seconds, the object moved 7.5 meters in the positive direction. Over the next second and a half, it moved an additional 15 meters in the positive direction. Over the next second, it moved 5 meters in the positive direction. At the end of that 4 seconds, it had turned around and it was starting to come back in the other direction. And it went 5 meters in the other direction as it sped up. And then it went an additional 10 meters in the other direction at a constant speed. If we want to know how far it went over this whole time period, we add all those numbers up. So we add 7.5 in the positive, plus another 15, plus 5 in the positive direction, and then minus 5 and minus 10. So this 15 and this negative 15 essentially cancel each other out. It moved this way and then moved back. And the net change in position for this particular object is 12.5 meters in the positive direction. Did I do my mental math right? Does that look okay? All right. And I'm going to show you next week how you can then take these displacements and use those to make a position versus time graph. We're missing a really key piece of information to make a position versus time graph, which is we don't know where it started. We know it moved 7.5 meters over this first 1.5 seconds, but we don't know where it started. So with a position versus time graph, we either have to be told where it started, or we can just say, oh, it started here, and then we calculate all of our positions relative to that starting point. Okay. All right. So at this point, what I'm going to do is turn things over to you. Here are the things that I'm going to ask. First of all, if you need a break, as soon as I shut up, this will be a great time for you to take one. Second of all, I want you to complete the motion match exploration activity to the best degree you can. You might not get everything done, and that's okay. You can still get full credit just by really locking in and trying to think about stuff and learn stuff. Remember that the work that we did in class on Tuesday, I answered some of these questions for you. So if you look at the motion match exploration activity, you'll see these questions. Number 5, this is what I talked to you about in class on Tuesday. So all of you should have this written down in your notes from Tuesday. And then if you get all of that done, then your next step is to do what I've been suggesting that you do, which is to really try to challenge yourself. Ask yourself questions. I gave you some examples on here. Like, for example, what do you suppose an acceleration versus time graph would look like? You can play around with those. We haven't talked about them yet, but you can certainly play around with them. And then you can do some practice. You can practice finding slopes. You can make a position versus time graph, use that, and try to construct the resulting velocity versus time graph, and then see if it matches up. And you can find displacements from a velocity versus time graph. So you're not limited to what I have here. I want you to be challenging yourself and thinking about what else you can do and what else you can learn, right? And then the last thing that I'm going to ask you to do, and I'll tell you to do this at about 11:15. I'm going to have you put your name on your paper. I'm going to have you take a picture of it and turn it into your canvas. And then I'm going to have you put your work in here. This is the new inbox, and hereafter this will be called the turkey bin, because this is the kind of thing that you cook a big turkey in. And back before Canvas, this is how I used to collect work. I'd forgotten about it, but I found it, and I'm really happy about it. It's kind of nice to have the old turkey bin out of retirement. Okay, does anyone have any questions before we start with a break and move on from there? Okay, all right, let me know if there's anything you need.